Okay, so here we'll do a quick review of this recursive sequence question that we were working on in class on Thursday. I guess the first thing I'd like to point out, and Eli brought this up, is that this notion of recursive sequences. Recursive is not a type of sequence. It's really just a way of defining. So let's just make sure we understand that. It's a way to define a sequence, and it's not a type. Like a type, arithmetic and geometric were types of sequences. You know, the numbers fit a specific pattern. Here, recursive just means that we're able to write any term as some function of, well, actually, I'll just say prior terms, because it could be more than one, like we saw with the Fibonacci, the way the Fibonacci sequence was defined. That's supposed to be an f there, f of prior terms. So again, just wanted to make sure that clarification was made more obvious, that recursive is not a type of sequence, it's just a way of defining it. And for example, we saw that arithmetic and geometric could both be defined recursively as well as explicitly. That's what we did in the very first lesson of this unit. Okay, so this example, we have a population of a certain country. It's growing as two conditions. Here we see that the population growth is in fact 1% of those already in the country. So we take whoever's there and they grow by 1% every year. And then we also get this immigration influx of 20,000. And when we see this is like an annual type of process. This is what should suggest to us that something recursively might be a good way to go. So the idea is that we want to model the population. We want to create a sequence of population. So for example, the sequence when we're done here, we'd have P0, P1, P2, P3, out as far as we want. So that's the idea here. We're creating this population sequence in this modeling problem. And often this idea of using sequences to do a modeling problem will come up a lot. It comes up in finance, comes up in physics. So this is an important process to make sure we understand. So the initial term here, now I know when we first started this unit we kept talking about P1 always being the first term. Turns out when we want this subscript to measure time units, it's often convenient to have that variable start with 0. So don't let that throw you in this problem, or sometimes we will think about having a 0th term. But we probably won't really ever have negative terms, like a p to the negative, p subscript -1, or a negative first term, for example. So here, this problem talks about the initial population being 5,000. So this first question is really just a matter of defining the start point. And remember, that was an important part of every recursive sequence. To define it, we need a rule for how we move from term to term, but we also have to know where we start. Otherwise, we won't know what the actual sequence is. So that's our starting point here. Pn, that's our population at the end of n years. So that's going to be our sequence. N again is the number of terms. So we want to write a recursive expression for this. Well, so what happens? Our population at any point in time is going to be a function of where we were. If we go back to the problem, it says we're going to grow at 1%. So the population is kind of like a bank account almost, or if we're going to grow at 1%, we're going to take just 1.01 times whatever the population was in the last period, and this would represent our new population being 1% higher than the prior population. If that's all that was going on in this problem, we'd be done, and that would actually be a geometric sequence in this case. But there's also this piece of the immigration where we have 20,000 people coming in, and so that's why we also have to get the new population for a given period, go ahead and add 20,000 people. So this would actually be our recursively defined sequence. We just take the prior population, multiply it by the 1.01 and add it. And the complete definition, actually, if I said completely define the sequence, you actually need to provide this piece and this piece, because without the starting point you don't know what the actual sequence is going to be. So in part C here, I'm asking you to calculate the population of the country at the end of the first 3 years by hand, just to go through the motion of doing the actual sequence. So we have P, we already know that, oh, what happened there? We already know that P0 equals the 5 million people. P1 then, we just go ahead and put it into this formula. P1, substitute n for 1, we're going to get 1.01 times P0 plus 20,000. So if we go ahead and just plug that 5,000 into there, we'll get 5,000, you go just put that in your calculator, you'll get this number. So this P1 would be the population after 1 year, and be this 5,070,000. Okay, what I've done here then is just gone ahead and done the rest of them here just to kind of walk through what's going on. So P2 then, I'm just going to plug that into the formula. It's going to be 1.01 times the prior value. And again, I have the prior value right here. Just going to go ahead and substitute that in there. Take 1% of that value, add my 20,000 immigration, and then I come up with this number. And then to get the population after the third year, I'm going to do the same thing. I'm going to go ahead and plug it into that formula, n equals 3. And again, it's just going to be 1% of the prior value, which I stick in there. 20,000, add my 20,000 immigrants, and then this would be the population after 3 years. So you can see why this lends itself nicely to a spreadsheet, and which leads us to the next two problems. So these next two problems, I'm just going to talk through them quickly, and then I'm going to pull up a spreadsheet that I did in Excel. I know I asked you to do this on your calculator, but I don't really have a good way to show that here on this computer that I'm using. So I think you'll get the idea of showing the Excel sheet, which is actually also posted on Edline if you want to go ahead and just look at that spreadsheet. So here, the idea is we want to use the spreadsheet to calculate the population at the end of 20 years. Well, this is really just a matter of finding P20 is what we would want. Now, one way we could do it is to go ahead and what we were just doing by hand, do that 20 times. Gets a little bit tedious, obviously, so we're not going to do it that way. And that's going to suggest using the spreadsheet. And this second problem here is we want to figure out when the population would exceed 10 million. So this is, we don't actually know the term. You know, there's some term number here that we're going to have to figure out, and we want to find that particular term number. And so we're going to visually inspect our spreadsheet to see when our sequence starts to go above 10 million, and then we'll be able to look up that particular number. Okay, so here's the spreadsheet. Again, the spreadsheet is posted on Edline if you want to pull it up and play around with it yourself here. But the idea is I'm just creating two separate columns here. The C column is just going to be my term number. It's going to start at 0 here, and then each row of the spreadsheet is going to be the next term number, and I've just defined that. If you look up in this little formula box up here, it says it's the cell above me plus 1, and then I go ahead and would copy that down, and I would be able to fill this row. And I just filled it down. It's kind of by 100 rows, or I'm not sure where it is, but I just copied it down a lot of spots, and then went over to determine to program the population column. So here, this is going to be our actual sequence, P of n, called population, and not surprisingly, we're going to populate that first cell with 5,000. I'm sorry, 5 million. Go ahead and type that in, and then I can just go ahead and create that recursive formula. And if I look at this first one here, you can just see it looks exactly like the formula we wrote on the notes page there. I'm going to take 1.01 times the cell above, so D3 is the one in the cell above, and I'm going to add the 20,000. And that's the recursive expression here. And because I'm using the cell above, it's like it is that I'm using the prior term to come up with it. And then from there, I would just copy that down to get P2, and I keep copying that down all the way, and then I have basically my spreadsheet with my population sequence, and I can just read that off here. So like you can see these first three here match the what we did by hand for P1, P2, and P3. So that gives me a lot of comfort that I've done it correctly. And then from there, I just need to, the first one was we wanted to figure out what P20 was, so I'm just going to go ahead and go down to the spreadsheet and find where n equals 20, which is this row right here. And the answer to that one would be 6,541,330. That's our answer to D. And then the E was just asking where did this population exceed 10 million. So you can see how we're going to do this. We're just going to keep scrolling down in our copied down formulas till we see the first instance where it goes above 10 million. And you can see that occurs at n equals 55, so we're going to say that 55 is the year after which 10 million is reached. So you can see at 54, it's just below, and then we cross over into 55. So I would consider the answer to that to be 55 years when this population would hit the 10 million mark. And that's it for recursive sequences. Hopefully that all made sense.